So welcome everyone to Guided Study Group week 13 of Statistic 100. And so today is going to be the final exam review for Statistic 100. And so it's going to be mostly on lesson 10 to lesson 12. And to kind of like review the stuff that we learned before midterm 2, please refer to the midterm 1 and 2 exam review, which I remember is week 5 and week 10 Guided Study Group. So today, we're gonna go over the main contents of lesson 10 to 12, and then we're gonna do some of the practice questions that I found in the practice exam. So lesson 10, confidence intervals. So the thing to care about in confidence intervals, and also the step to identify what is the confidence intervals for some statistic and parameter. So first of all, determine the parameter and statistic. So say if you want to find a confidence interval for the population mean, then the population mean is going to be the parameter, and the statistic that we use to estimate this confidence interval is going to be the sample average. Then check for the applicability of normal approximation. So to find the confidence interval using Z star as the multiplier, we need the problem to be normally approximate. In other words, we need the distribution to be approximately normal, which we need to check for independent trials and large sample size. Then we estimate the standard deviation of the statistic of standard or the standard error. So kind of like based on the sample data and the sample standard deviation, then we use that and depending on what sample size we use to either bootstrapping or find the distribution of the mean of the populations, we're going to calculate the standard error. Then we compute the statistic plus or minus Z star with the standard error. In that case, we're going to get the confidence interval for the population parameter. Note here that the Z star multiplied standard error is the margin of error. So in any case, when you are asked about a margin of error from any kind of questions in the exam, know that it is the product of the multiplier and standard error. Lesson 11. So in lesson 11, we talk about hypothesis testing. And so the step to do that is first determine what is the parameter of interest. Is it a mean, proportion, difference between means or proportion? Then write the known and alternative hypothesis as statement about this parameter. Then in the second step, we determine the sample statistic and its distribution if the known hypothesis is true. In some cases, and usually that's the case for our class, if it's normally distributed, calculate the standard score. Then determine the likelihood of each outcome and use the table to find the p-values. And so this one will depending on our alternative hypothesis. Is it a one-sided or is it a two-sided? Then we're going to consider what is the p-value. As I mentioned like last week, where in the week 12 Guided Study Group, where we talk about hypothesis testing and things about the probability of different testing, one-sided and two-sided. Then we make the conclusion corresponding to the result of the comparison between the p-value and the confidence level. To say if you get alpha level or what the threshold for a significant test is 5%. So when p-value is smaller than this, then you have a significant test result. Now lesson 12, which is also the last piece of materials that we have here, is some cautions about hypothesis tests. So the first one is the large sample. As we mentioned last week, significant result based on large sample may not be of practical significance. So say when you have a large sample, caution, the result that we have in large sample may be of maybe significant, but it's of small difference with the estimate. And so they are of little practical significance. Then we have small sample caution, where the results are not significant in small sample, may still be of practical significance, and that is may be of some of the hidden variables that we haven't considered in our test. And finally, it's the multiple testing caution. So when you do a lot of tests, say 1,000 or 10,000 tests, then some individual tests may be deemed significant just by the probability of being deemed significant and not because of the true natures of the variables. Then finally, we have the human subjects issues. Because a lot of statistic tests, especially the field of biostatistics, where we try to figure out the chance of success from new drugs or new medications, we need to care about physical harm, try to avoid that, maintain voluntary participation, protect vulnerable populations, and ensure informed consent, regardless of whether the studies is beneficial to their subjects or not. Now, with that in mind, these are the formula that we use to calculate the standard error that we mentioned in lesson 10 and 11. If you have the mean or like a quantitative samples, then we get the standard error of the mean when you do bootstrapping or kind of like find a distribution of the mean. Then the standard error of that distribution is going to be sample standard deviation divided by square root of a sample size. Then we have standard error of a proportion, which is going to be the proportion, square root of proportion multiply 1 minus proportion divided by sample size. Then we have standard error of the difference between the sample values from two independent samples, which is going to be the kind of like similar to the Pythagorean theorem, where you have it equal to the square root of standard error of the first sample and then the square of the standard error of the second sample. And then finally, if the normal approximation applies, we also have the table of multiplier numbers from the normal distribution corresponding to different confidence levels. So 95%, 90%, 99%, and 80% all have different multipliers, and hence they have different margin of error, even though they're talking about the same sample. So standard error in that case, standard error is going to be the same, but the multiplier is different. And the higher the confidence level, the bigger the multiplier. Therefore, you have bigger margin of error. Now, with that in mind, so let's now working on the practice questions and problems that I got from the practice exam. And so I did the exam this morning, and I found these problems kind of like challenging, and I think some of you might get it incorrect when you try for your first attempt. So maybe we can go through them together. Or if you want to work on it alone, please feel free to mute me anytime. So the first question has two parts. If a statistical hypothesis test turns out to be significant, then it's not possible to make a type 2 error. Is it true or false? Well, so let's say when you have a statistical hypothesis test turn out to be significant, and type 2 error is where you fail to make a conclusion that the test is significant. So if you already concluded its significance, then you cannot make a mistake of not concluding it to be significant, right? And so the answer is going to be true, because just simply when you already conclude that a test is significant, you cannot make a mistake of missing to conclude it. And so here, this question tries to address us and reminds us about what is the type 2 error, and kind of like relates to the conclusion of the statistical test. Then the next part, in which situation would the standard deviation be 0? So let's think about standard deviation first before looking at the answer choices. Standard deviation measures the variability of the points of the populations from the mean of the populations. And so to have 0 standard deviation, it means that there's no variability at all, which also means that all of the values in the population or the samples are equal to one another. And so the answer is B, when the numbers on the list are all the same. when the height is wrong because the height of the bar in the histogram, even if they are the same, it only means the fact that there's still some different values. So say 1, 2, 3, 4, 5, which means that each of them you're gonna have a different values, and there's still some variability. Then C is wrong when the histogram is symmetric and half the values are positive and half the values are negative. And so this is also wrong because there's still some variability. If you look at the populations here, like this, they still vary from the mean. The mean here is 0. And so the variability is only 0 when you have only every point on the same straight line. And so C is also wrong, and then D is also wrong because the median and the mean doesn't have anything to do with the standard deviation. Because it's still depending on all of the values in the data set. Now let's look at question 2. Again, mute me anytime if you want to work on it on your own. If you select a college student at random, then whether they are engineering majors and whether they are female are independent or mutually exclusive, or both or neither. Now, let's look at engineering majors and female. So let's think about mutually exclusive first. Sorry, mutually exclusive. They are not mutually exclusive because the definition of mutual exclusiveness is where you have two events cannot happen at the same time. Well, obviously we can have female students and also in engineering majors, so both of them can happen at the same time. So any answer with mutually exclusive is not right. So A and C are not right. Now let's look at B and D. Are they independent? Well, technically for every single majors, male and female are independent in the chance of being in that major. And so the major and the gender technically doesn't have anything to do with one another. However, in reality, let's consider this. The engineering field and the business field actually have an impact on whether on the female proportion. And so usually in the female proportion, it's considered as the male dominant field. No, in the engineering majors, it's considered as a male dominant field. And so there are usually fewer females than males in the engineering field than compared to other fields. And so in reality, these two events are not independent of one another. And so D is actually the correct one. So technically consider they are independent between majors and gender are independent, but in reality it is not. And so question 2, the answer is D. Now let's go to question 3. A researcher wants to find out what genes in the body are associated with surviving the Ebola virus. Blood samples are taken from 20 people who contracted Ebola but survived, and from 20 others who died from the disease. A microarray is used to test 10,000 different genes simultaneously to see which ones have significant elevated RNA expression compared in the survivors versus those that died. Now, the problem with this study is that, now, before we think about the problem, let's summarize what we have from the study. We have 20, the sample is 20 with Ebola and 20 without Ebola. So, no, the one who 20 that survived and 20 who died from it. And so, in that case, our sample is only 40, and you have two groups, 20 for the control groups and 20 for the maybe the treatment or something, or like 20 who survive and 20 who die from it. Now, we are going to do 10,000 tests simultaneously. So the number of tests is 10,000. And compare the genes, the RNA expression in each of the genes between the two groups. So compare the RNA expression. Now, the problem with this is that you have 10,000 tests and a small sample. So let's see what we have. And with such a large sample, they may find important genes to be significant. Now, the thing with large sample and also the consider the large sample rule that we have when we talk about in lesson 12 is that with a large sample, you can detect even small difference or like small departures or like small significance that we cannot detect in the small samples. And also just consider here the sample is not even large, it's a 40 people, so A is not even right. And for A, even if we have a large sample, we should correct A as with such a large sample they may find small genes or like unimportant genes to be significant, because that's what is the large sample caution said. Now B, if they use the traditional definition of significance, they would expect 500 false positives. And so this is the correct answer, as it follows a multiple testing caution, is that when you have 10,000 tests and you use the traditional definition of significance, which is the 5% confidence level, then you would expect 5% of 10,000, which is 500 false positives. Now let's consider C. Many of the genes are not independent of each other. Now, I am not an expert in biology, but I know the fact that they can be independent or they can be not independent. And so it's like a 50-50 chance depending on each of the genes. And so we cannot make a conclusion that this is the problem of this study because many of the genes are not independent of each other. We can select maybe 10,000 of the independent genes in the human DNA collections, and so C might not be a problem of this answer of this study. And now last one, the standard deviation of the expression level may vary from one gene to the next. Well, this is for sure because, well, I mean, each of the genes can have its own standard deviation and mean, and so, but each of the tests are done independently, and so they might not be a problem with one another at all. It just make our calculations maybe a little bit more complicated. But now we have computers, and so computations and automation make everything much easier and faster. And this is not a problem of this study. So D is also wrong. Now let's go to question 4. Again, mute me if you want to work on it on your own. Correlations will give a deceiving impression of the strength of an association. A, when the pattern of the points in the scatter plot is not linear. Now, we use correlations, and from the scatter plot is where you make assumptions that the relationship between the two variables is linear. But when the pattern of the points in the scatter plot is not linear, correlations might not be used because it is not a suitable parameter to use to show the strength of the relationship between the two variables, because correlations is define and compute and making the computer based on the linear relationship assumptions. So A is wrong. Now let's look at A is the answer, and let's look at the rest of the answer. When X and Y variables have negative association, well, when you have correlation, it can be positive or negative. It can be a strong or it can be a strong direct or strong indirect or strong positive or strongly negative relationship. And so B is correct, and it is not a reason to give that correlations give a deceiving impression of a strength of the association. Now C, when the standard deviation of both X and Y are large, the correlations is calculated based on the standard deviation of both X and Y, and so it shows kind of like it is in the formula of calculating correlations. And so standard deviation doesn't really affect the validity and reliability of the strength of the correlations. And so C is also wrong, and then D is also wrong because all of the above. A is correct though. There's another way that correlations will give a deceiving impression of the strength of an association. That is where you have first one is where you have the nonlinear relationship. The second one is where you have outliers. So outliers is where it will create, or like increase and decrease the correlations, coefficients, and so that can give a deceiving impression of the strength of the association. And now is question 5, which is also our last questions for this course. The EPA sticker for a particular model of automobile claims the car has average highway mileage of 40 miles per gallon or mpg. A consumer advocacy group claims that the manufacturer did not test the mileage under proper conditions and that the true mileage will be worse. So will be worse. And so our known hypothesis is that where you have, say, average is mu equal to 40 mpg. And so HA, alternative hypothesis, is going to be worse than 40, which is mu smaller than 40. A random sample of 36 of these cars, n equals 36, are tested and found to have an average mileage of, so X bar is 38.7 mpg. That is a sample statistic and a standard deviation of 3 mpg. Now let's carry a significance test. So first of all, we identify the known and alternative hypothesis. Then for B, we find the measures of variability of the average mileage under the known hypothesis. And to find that, we use the concept of standard error of the mean. And I already have the formula for that in the last slide of our final exam review, which is going to be the standard deviation of a sample divided by square root of n, which is the sample size that we use. So here we have 3 over square root of 36. We're going to give us 3 over 6, which is 0.5 mpg. Now part C, what is the conclusion of this test? And so if we find the standard score, so I will find Z here that we have is 38.7 minus 40 divided by 0.5, and it gives us negative 2.6. Based on the probability table for normal approximation and multiplier, we have the p-value equal to the probability of Z smaller than negative 2.6, as I mentioned last week in lesson 11. When we talk about hypothesis testing and the alternative hypothesis is smaller than, then you need your probability, your p-value is going to be the probability of your Z standard score less extreme, which is going to be small. No, the p-value is going to be the probability of your average, sample average be more extreme, which is going to be Z smaller than negative 2.6 in this case, because the alternative hypothesis is mu smaller than 40. And so that is going to give us approximately about 0.5%. And so the conclusion is that this is significant. And based on the sample, the average is actually smaller than 40. So we recheck the known hypothesis. Recheck H0. Now let's see part D. Does the confidence interval of the true average MPG of the model car covers 40 MPG? Now in this case, because we already make a conclusion that the actual average of the population is smaller than 40. Therefore, the confidence interval will not cover 40 mpg, because this is the confidence interval, which is going to be the most likely interval that our average is going to fall into. And so because we just conclude that our actual average is smaller than 40, then the confidence interval will not cover 40. It's going to be less than 40. And so our answer is that it will not cover 40 mpg. Now that ends my last sessions for Statistic 100. If you want to access all of the weekly review, please visit my YouTube channel. Any questions, last minute questions before the exam, email me at my usual email. And I wish you guys luck for the exam. It's been a very great semester, and it's been my pleasure to be working with you guys. So I wish you success in the near future and also in your long-term future. And I hope to see you guys one day in reality. Have a great weekend and a wonderful exam. Thank you for listening.